Okay, so we have like this thing here. And we have this thing here. And we have these, I'll just draw them as little lines. We have 4, 2, 3, 4. And wherever these, I should have made them a different color. So wherever the red crosses the square, that forms a transistor. And if you look at this bottom one here, let's make a blue here. We have a blue here. And the top blue is VDD, and the bottom blue is ground. So, and the squares are their contacts, okay? So if blue crosses over those squares, it makes a connection to this square boxes. So eyedropper. So look, let's look at this bottom one right here. So there's a connection right there to VDD. And then this basically, that connects the square below, and then it goes through all these transistors.
Okay? So that one's like 4 transistors in series.
Yeah, so that's like, and those are PMOS, 1, 2, 3, 4. And then this one connects this one to there. See that? So that's like making a connection to the NMOS. And in the NMOS, there's a little connection here to VSS. There's a little connection here to VSS. And then this thing, which is going to become the output, goes all the way across there. And it connects to that, and it connects to that. So if you look at right here, see there's a transistor here. Let's call it. There's a transistor right there. And there's a transistor right there. But if you look at them on each side of them, they're connected to this thing. This is going to be called our output. And on the middle, they're connected to this ground. So that looks like 2 transistors like that. Connect to the output and then connected to ground. And these other 2 are the same way. They have 2 connected to the output and they have 2 connected to the ground. So there's another 2 like that. And those are all NMOS. And so that whole thing, and then this is like A, B, C, D. This is like A, B, C, D, A, B, C, D. And this is our out. So that's an OR gate.
Cool. I understand now. Thank you very much.
And if I just rearrange the metal, I can make NAND gates. I can make all kinds of different stuff just by rearranging the metal connections. So I don't need all the layers below. All I need to do is make metal connections.
I see. Thanks.
Okay. Let's make this bigger. Okay, 8:36. I guess we can get going. Got a few more people here. Let's go to here. Yeah. So we're on March 17th. So we're on week 9, and we didn't finish. We're going to finish digital circuit implementation today. There's only a few more questions, and we're going to have some bonus questions, or a few more slides. We're going to have some bonus questions, and then we're going to start asynchronous today. That is the plan. So we're going to go back to here. We did a lot of talking last day. Wow. Talked straight for an hour and a half. But we covered a lot of stuff. So I think this is where we ended up. We talked the whole idea about non-recurring engineering, recurring engineering, and how if you have a lot of parts, it's better to do an ASIC. If you only have a few parts, it's better to do an FPGA. The next thing is this is kind of old. This is like 2011 prices, but the pricing is still about the same today, except that the FPGAs are much bigger than what's shown here. But this is the Vertex 6 family, which is one generation before the ones you guys are using in the lab. A couple things to note here. So this first group is like a low end. These have 240 IOs and they have 75,000 logic cells. And they also have a speed grade. And I guess as it gets more negative, it means it's a faster speed grade. And there's a breakdown here of cost of the part. And there's a cost per logic cell and the cost per IO. But you'll see as you increase the number of the speed, it goes up. This is $625, $725. That's just for one part, $1,000. If you make it more IOs, and it goes up in cost, 718, $899, $1258. So that's like showing the effect of number of IOs because it's a bigger package with more connections and more functionality. So they increase the cost. This next group of three shows the difference with, this is a bigger part. So it's got 10 times as many logic cells. It's got about 750,000. And it has a large number of IOs, 1,200 IOs. So that's a really big package. And again, it goes up with speed grade, but these things are expensive, 15,000, 19,000, 20,000. So I'm saying the really big FPGAs, like $10,000 is not uncommon. This is at that time, this was the biggest one you could buy 750,000 logic cells. And then this is sort of a low end Spartan 6. This was kind of before Vertex 6. And this only had 100 IOs. It had 3,000. So that's like 1/10 of this other one or even less. So relatively small number. And they were down like $12, $10, $11, $13, so on. So you can see there's a wide range of costs from tens of dollars to hundreds of dollars to thousands of dollars. It just depends on how many IOs and how many logic cells that you want. Now this is pretty old in comparison. Like the top end of this is 2011. The top end was like 750,000 logic cells. And if we back up here to our little slide. This is what you're using in the lab. So this is 300,000 logic cells. So about half as many in the lowest end of the Vertex 7. And this low end Vertex 7 is what you're using, which would have, you're looking at maybe $100. So the prices, basically the prices are kind of like similar, but you get like today's FPGAs will have like 10 times as many logic elements as this table here. And that's just Moore's law. As we shrink the technology down, we're able to pack more stuff onto the die. Okay, so that's just a little breakdown on FPGA costs. Applications. So as I said, ASICs are used for like really high volume things like consumer electronics, like laptops and cell phones and so on, mobile phones, computers, digital cameras. They all have custom ASICs. Whereas FPGAs are using more lower volume products like industrial military electronics, like a base station, a factory automation, internet, cloud routers, glue logic. I don't know, do you guys know what glue logic means? Glue logic? No. Glue logic is like, it's a very common use for low-end FPGAs. Let's say you got a board, and on your board, like for instance, our FPGA board, there'll be like an Ethernet controller. There might be a memory, external like SRAM or something. There might be, a microprocessor. You might have a USB chip here. You might have a UART. I don't know. A UART or something. I don't know. But anyway, these things are all connecting to outside. But inside here, sometimes like the microprocessor might access the memory and it needs to access it with an active low signal. This is a write bar, but this memory has a write signal and you need a little inverter here to draw that. And maybe this Ethernet controller, oh, you know what? I need a decoder to pick the right address here. I need a little decoder to go from like 2 bits to 4-bit, 2 to 4 decoder to access that Ethernet controller. You might have all kinds of little things here that you need to, just to get the signals correct into all these other external peripheral chips. Well, rather than actually put discrete parts on there, people, what they do is they say, oh, you know what? I'll take this thing, I've got my Ethernet controller, I got my memory, I got my microprocessor, I got my USB controller, got my UART, and I'll say, you know what, I'll just put a little FPGA. My FPGA does all this stuff. It makes all the connections to all these things. And that's what we call it glue. It's gluing all these things together. It's called glue logic. Very common thing. You don't need a lot of logic, so these are usually low cost, little simple FPGAs, but very common. In the old days, we would put discrete parts down, but nowadays we just put it in an FPGA. So that's glue logic. So these are all kind of uses of FPGAs. Last slide. This last slide is related to how much money you can make from selling chips, okay? And what this shows is, this is time here, and it's measured in quarters. In business, we usually measure things in quarters, like Q1, Q2, Q3, there's 4 quarters per year, because they kind of align their books at the end of the quarter, they figure out how much money I made or whatever. And the y-axis is how many sales you have. Well, there's 2 curves here. One's a purple curve and one's a red curve. And the purple curve is the example of a company that was the first to have their product. You know, like say you have a new phone and they said, you know what, here's the first phone that has a 8-core processor. And this company in purple came out with it first. And then there's a company in red and they came out with it a little bit later. You know, they're half a quarter later, 2 months later. Well, the first company, what happens is your sales go up. First, you start out no sales. Your sales go up very fast, okay? If it's a popular product, and you're selling it, because when you first come out, it's worth a lot. Like if you buy a new iPhone, I don't know what's the latest iPhone, X11 or 12, I don't know. You know, you pay like $1,000 for it, right? Or $1,500, some of these phones are. But if you go buy an iPhone 6 today, it's like $100, right? So when it first comes out, it's worth a lot. But over time, it's less popular. It becomes a commodity, we call it. You know, everybody can get one now. They become really cheap, okay? And so what happens is when you're selling it for a high cost, your sales go up and you get very high sales dollars and you hit a peak. And then as the price comes down, because other companies are producing similar products, or, you know, you have a newer product that's much better than the old product, then the value of it goes down, and eventually the sales of it go down. And eventually it's the end of the product, because nobody buys an iPhone 4 today because they're useless, right? So eventually iPhone 4s are worth nothing. So this purple curve shows, you know, this is an early adopter, first company to come up with a product, this is how much money they make. The red curve is a company, oh, they're a little bit later. Like, you know, maybe Android came out with a phone that had a 16-core phone, and they were 2 months later, maybe it was Samsung or whoever. They go up fast too, but by the time they hit their peak, you know what? It's becoming very common, and they don't get as high a peak, and then they go down to 0 as well. And the difference in here, which is this green shaded area, says, you know, that's the extra money you make from getting to market early. So there's always a huge amount of pressure on particularly consumer products to get the product out as fast as you can, because you're going to make a lot more money if you get to market early rather than late. And so that drives the consumer market. You know, every year, every second year, we get a new phone or new product. Any questions about that? Nope. Okay, that's the end of those slides, I do believe. Now it's bonus time. Bonus time, bonus time, bonus time.